Welcome to this class. In this class, we'll discuss about the equivalence of shear to extension and compression. So I have already drawn a figure here. So let us consider a cube of length L. So for the sake of simplicity of our discussion, I have just considered the front face of this cube as shown in this figure. So let us assume that this A, B, C, D is the initial shape of front face of the cube. Now what we are going to do here, this bottom surface of this cube here, this edge CD of this front face is in contact with the ground, and let us assume that it is fixed now. So it is not going to move at all, right? So then we'll move certain kind of tangential force in this particular direction on the top surface AB. So as this bottom surface is fixed, this top surface AB will shift and will assume a new shape as shown in this figure, A dash B dash. So what happened here actually, initially the front face was A, B, C, D, and CD surface, the bottom surface was fixed. Now due to the application of tangential force on it, on the top surface of it, it has assumed a shape of A dash, B dash, C, D. Okay. Now if you look at the diagonals, now initial diagonal AC got shifted to A dash C, sorry. AC got shifted to A dash C, and the DB, the another diagonal, got shifted to DB dash. Again, if you look at the figure, AC, the length of AC is more than A dash C. So what we can conclude from this, the length of initial diagonal AC is now reduced. So as this length is reduced, I can say this is kind of compression, because in compression, the length of fiber is going to decrease, right? And if you look at the diagonal DB, so initially it was DB, and after the application of tangential force, it has become DB dash, which is now increased. So as the diagonal length DB is increased, I can say this is under tension. So in this particular example, by the application of tangential force F on the top surface of the cube, I have seen here that one of the diagonals is under compression and another diagonal is under tension. So that's what we are going to see here. This shear is basically produced by the application of tangential forces, and this produces extension, which is a tension, and compression simultaneously. And now this is what we are going to study, and how much tension, how much tensile strain, how much compressive strength it produces, we are going to see it. Okay, so let me consider the first diagonal AC. So if I consider diagonal AC, okay, so initially the length of diagonal, so as I assume the length of this cube to be L, so the diagonal length will be L times root 2. Okay, now I have to find its changed length A dash C after application of force. So let me draw a perpendicular from this A dash point, because this C point is anyway common, right? So let me draw a perpendicular from A dash to this particular initial. So this is kind of perpendicular. Let me name these. What should name this? Let me name this as P. So now I have drawn A dash P is basically perpendicular to initial diagonal AC. Now, as this angle, because due to the application of shear force, now this has changed a little bit, and let me take this angle to be theta and assume that theta is very small. So it means that due to application of tangential force on the top surface, it is not going to distort by much angle. This angle by which it has distorted is not very large. It is always very small. So as I assume that this theta is very small, I can say that the length of A dash C, is approximately equal to PC. See, in this triangle, basically, as this is right angle triangle, this A dash PC is a right angle triangle. This is the length of PC and A dash C will never be equal, right? But what we have assumed here, the theta, the angle by which it has distorted, is very small. That's why I can assume that the length of this PC and A dash C, these lengths are more or less same. Okay, so if I want to find the change in length, so let me find the change in length. Change in length. So this change in length is final length. This is A dash C minus initial length AC. So I can replace this A dash C by this PC minus AC, which is nothing but minus of AP. And why this minus sign suggests? This minus sign suggests that it is compression. This minus sign suggests it is compression. So let me take the amplitude. So sorry, the magnitude only. So the AP, let me consider the value of AP now. Let us say that this top surface has shifted by length small l. So this is also small l, this is also small l. So this, let me write it here, A dash and B dash, by which it has shifted is small l. Okay, so if you look at the triangle A dash, this angle was 45. This angle was 45 because it is a cube, right? So this cube diagonal makes angle of 45 degrees, and this A dash is kind of hypotenuse in this particular small triangle, right? So I can write this AP, this length is L divided by root 2. Basically it is L sine 45, L cos 45 kind of thing, and both are same 1 by root 2. So I have written this down. AP, change in length, I have got as L by root 2. And let me find now the strain. So this is compressive strain because this is under compression. So this is compressive strain, and this is equal to change in length. This is AP divided by the original length diagonal AC. So I have got this L divided by root 2 change in length divided by capital L times root 2. So if you look at this particular thing, simplify this, you get L over 2L. L over 2L. So let me name this equation 1. Okay, so now we have seen the treatment for the diagonal 1, which is AC, and it is under compression. Now let us take the diagonal DB. So another diagonal, now it is DB. So again, the length of diagonal DB is again L times root 2. Again, to find the change in length, let me draw a perpendicular from this D point is anyway again common. So let me draw a perpendicular from this point P on DB dash. Okay, because now the increased length is DB dash now. Let me name this as Q. Now I have drawn a perpendicular from point B on new diagonal DB dash. Okay, again I have assumed that this angle is also theta because it is also shifted by L. So this angle is small. So the angle by which this basically this diagonal gets distorted is actually small. So if you look at this particular angle, you'll get to know what is that angle actually. And if you see particularly this angle, this is very small. Okay, so as these angles are small, I can assume that the length of DB and DQ. So theta is small. Again, let me write theta is small. So I can assume that the length of DB is approximately same as length of DQ. So again, change in length. Let me find the change in length. So change in length is equal to final length DB dash minus initial length DB. Now DB dash as it is, let me write DB dash minus DB, I can write approximately equal to DQ, and DB dash minus DQ gives me B dash times, sorry, B dash Q. And again, if you look at this small triangle BQB dash, this angle is also again, sorry, this. So again, see, this angle was 45. Here, this was 45. But as this theta is very small, so this is very close to 45. Though it is not 45 exactly, but I have assumed that this theta angle is very small. That's why I can assume that this particular angle B dash Q is approximately equal to 45. Then again, due to this assumption, we can say that the change in length B dash Q will be again L by root 2. And now if I want to find the strain, it will be tensile strain. It will be tensile strain. Why tensile strain? Because the length of the diagonal DB is now increased. So what is the formula? Change in length, again B dash Q divided by original length DB equals to again L over root 2 divided by L root 2. So again, I'll get L divided by 2L. L divided by 2L. So what we have got here, let me revise it quickly. So initially it was a cube. I have drawn a front face A, B, C, D. The bottom surface was fixed. Now I have applied a tangential force on the top surface AB, and now it has shifted to A dash B dash, right? So the shifting of the top surface is by distance small l. Capital L is the length of the cube, and the angle by which it has distorted is very small, right? So then I have drawn two diagonals of cube, or let's say front face, and observed that one of the diagonals has decreased in length and the other has increased in length, which means that one diagonal is under compression and another diagonal is under tension. So due to the application of tangential force, I am observing both tension and compression simultaneously in this particular face, right? So then I have decided to find the strains developed in both diagonals. So I have obtained a compressive strain by certain assumptions like theta is very small, that it is equal to L over 2L. And similarly, the another diagonal which is under tension, it has produced equal tensile strain. So now again, if you look at this particular figure, so this distance A dash is L, and this small distance, the another distance AD is your L. So if you, in this particular figure, so just I'm going to erase this figure. So for the reference, you note this down that your compressive strain and tensile strain both are L over 2L. And this distance was L, and this distance AD was your capital L. Okay, so let me write this. So let me draw this triangle only, A dash D, and see what happens here. So I have obtained compressive or both tensile strain to be equal to L over 2L. Now let me draw this particular triangle over here. This was your A, this was your A dash, and you had this side of cube which is capital L. So this is L. For the sake of simplicity, let me draw a little bigger triangle, though I have assumed that this theta is very small. Okay, anyway, that's fine. So this angle I have assumed a theta, and this is definitely a 90-degree triangle. So this is basically a right angle triangle. So what I get over here, so if I take tangent of theta, I get small l over L. And as I have assumed theta is very small, for theta to be very small, this tan theta is approximately equal to theta. So from this, I can write that this theta to be equals to, theta would be L over capital L. And if you look at this compressive and tensile strains, so I get here compressive strain to be equal to theta by 2, and simultaneously the another diagonal produces a tensile strain of the same magnitude, theta by 2, and by the combination of this compressive and tensile strain, I produce a shear strain. So shear strain, we have seen the basic definition of shear strain. What is shear strain? The angle by which the face is distorted. The shear strain is basically theta. So from this, we can conclude that the shear strain, shear strain produced is a combination of tensile strain produced in one of the diagonals, as well as the compressive strain produced in another diagonal. So that's what we have started from, right? So we have started from the equivalence of shear with extension and compression, which means tension and compression, right? So I can write this as shear is equivalent of tension plus compression together. And vice versa is also true. If your object is under tension and compression simultaneously, you can say that it is under shear. Or if your object is under shear, then it will have a tensile strain as well as compressive strain, right? So we can conclude that shear is equivalent of tension and compression, and the total shear strain produced, this theta, which will be equal to the tensile stress produced to theta by 2 plus compressive strain produced to theta by 2. So this is basically the addition of both. That's why we can conclude from this that shear is equivalent of extension means tension, extension and compression. I can conclude that shear is equivalent of extension and compression. And vice versa also, you can say that if your object is under extension and compression simultaneously, you can conclude that it is going to be under shear. So this is valid for solid objects. So what happens if you take a fluid? Suppose if you have a fluid over here, so this is, let's say, ground, and you have certain fluid at rest. Let us assume that you have no walls over here and it is at rest for the assumption. So now this is fixed. So as the fluid layer in contact with this solid is not going to move at all, that's why the velocity of fluid in contact with this solid surface, ground surface, will be zero, which we always call a no slip velocity, right? And if you apply a tangential force over here on the top surface, this fluid, not necessarily liquid, it can be a gas as well, when fluid is subjected to tangential force, or let me call this as a shear, when fluid is subjected to shear, it cannot sustain this shear stress and it will start to move. It will start to move. Though this layer is fixed, due to application of shear force, it will move, it will start moving with certain velocity. The velocity of particle below this will be little smaller. Again below, again smaller. At the point of contact, it will be zero. So if you look at the profile of the velocity throughout the thickness of the fluid, so the top surface will be moving with the maximum velocity possible. The bottom will be little less, again less, again less, and at the contact, it will be zero. So it will be kind of linear profile. It will be kind of, and this is ground. This velocity is zero, and this is certain velocity v. So what I mean to say here, when fluid is subjected to shear, unlike solid, as solid has just distorted and it has not moved from one place to the other place, it had just distorted or deformed and assumed a new shape, and our bottom surface has still remained in contact with the ground and it is still fixed. But in case of fluids, when you apply shear stress on the fluid, it cannot sustain that shear stress, and by the application of shear, it will start to move, unlike solids. Okay, so this is all about the equivalence of shear with the extension and compression.